This new concept, complete matrix space. So we know that every convergent sequence is Cauchy, but every Cauchy sequence need not be convergent. We have discussed its proof also, right? See, but now if in a matrix space XD, every Cauchy sequence is convergent, then it is said to be a complete matrix space. I will repeat, if every Cauchy sequence is convergent in a matrix space XD, then XD is said to be complete matrix space. Okay, so let us see a few examples of complete matrix space. Make a screenshot of this definition, then we will go further. See, now we are going to discuss these examples. In the example, we have to prove that RD is a complete matrix space where D is a usual distance. Okay, see, how to prove that it is a complete matrix space? Complete matrix space means every Cauchy sequence is convergent. So I have taken one Cauchy sequence Xn. So simply we have to prove that it is convergent, then we can say yes, R is a complete matrix space, okay, with a usual distance. See, I have taken a Cauchy sequence here. So my first target is to prove that it is bounded. What we have to prove? This sequence is bounded. So let us prove. So it is a Cauchy sequence. So therefore, for given epsilon, so I am selecting epsilon is equal to 1, there exists and belongs to set of natural number such that d, here we have to take mod, okay, since d is a usual distance, mod xn minus xm less than 1 for all nm greater than or equal to capital N. By definition of Cauchy sequence, we can write. So what will I do? Here n and m are any arbitrary natural numbers but greater than capital N. So in particular, I will take m is equal to capital N. So in particular, I am taking m is equal to capital N. So xn minus x capital N less than 1 for all n greater than or equal to capital M, since now we have fixed m. Okay, so see, what I will show you what is happening actually. So we have a sequence x1, x2, x3, so okay, and so on. There is some xn, next xn plus 1, next xn plus 2, and so on. There are some terms. Okay, so what we are saying here, distance between xn and the next numbers is less than 1. Okay, the distance between this xn and remaining elements is less than 1, but we are not talking about previous elements. So what will I do? Let m is equal to maximum of, I am going to consider the previous elements also, mod x1 minus xn, mod x2 minus xn, and so on. I will write here mod xn minus 1 xn, getting, comma 1. Since for remaining elements 1 is enough, since we know that distance between the remaining elements and xn is less than 1. Okay, so 1, and I have considered remaining elements. So therefore because of that we can write, so therefore mod xn minus x capital N is less than or equal to capital M, and now this is true for all n belongs to natural number. Okay, so this one was true for n greater than or equal to capital N, but now we have proved it, this is less than or equal to m, for this is true for all natural numbers. Getting? So very important thing we have. Now consider, see what I am going to consider, mod xn minus xn. Any nm belongs to set of natural number. I am going to use triangle inequality. So this is less than or equal to mod xn minus x capital N plus mod xn minus xn. This is triangle inequality. Okay, so this one is less than or equal to capital M, and this one is also less than or equal to capital M. Since this is true for all natural numbers, so you take n, you take m, you take k, whatever you want you can take. So this is equal to m. So therefore mod xn minus xn, okay, this is less than or equal to 2m, and this is true for all nm belongs to set of natural number. So what we get, this is definition of bounded sequence. Therefore sequence xn sequence xn is bounded. Sequence xn is bounded. Okay, so there is no more space, so make a screenshot of it, then we will go further. See, but we know that every bounded sequence has convergent subsequence. Every bounded sequence of real numbers has convergent subsequence, and our sequence xn is bounded. See, therefore xn has also convergent subsequence. So I will mention, therefore sequence xn has convergent subsequence. Okay, therefore sequence xn has convergent subsequence. Say xnk. I am calling it as xnk, and it converges somewhere. No? So it converges to x. So we started with a Cauchy sequence first. Getting, we proved that it is bounded, and we know that every bounded sequence of real number has convergent subsequence. Therefore sequence xn has convergent subsequence xnk, and it converges to some point. I am calling it as x. So now I will prove that the original sequence xn is also converges to x. So in this way we will prove this theorem, okay, or prove this example. So what will I do? I am taking one epsilon first. So let epsilon greater than 0 be given. So the basic information we have that sequence xn is Cauchy. We have, I will write, we have xn is Cauchy. You are familiar with definition of Cauchy sequence. So therefore what can I write? Therefore there exists n1 belongs to set of natural number such that mod xn minus xm less than epsilon for all nm greater than or equal to capital N1. I am calling it as 1. See, but small adjustment I am going to do, that is, instead of epsilon I will write here epsilon by 2. The second information we have just now we have got, that is xnk converges to x. We have xnk converges to x. So therefore for above epsilon greater than 0, there exists n2 belongs to set of natural number such that mod xnk minus x less than epsilon by 2 for all nk greater than or equal to capital N2. This is, I will call it as 2. See, 1 is true for n1, 2 is true for n2. So I will select maximum. Let n is equal to maximum of n1 and n2. So that means 1 and 2 will be true simultaneously for this n. So now consider, okay, so for n and nk greater than or equal to capital N, consider, I am considering mod xn minus x. Since our target is to prove that sequence xn is Cauchy and converges to x, so that's why I'm starting with this one. We have to prove that it is less than epsilon, then we can declare yes, sequence xn is convergent sequence. Here I'm going to use triangle inequality. So this is less than or equal to mod xn minus xnk plus mod xnk minus x. But see, here m we have, here nk we have, doesn't matter, okay, both of them are suffix. So this is less than epsilon by 2, so I can write this is less than epsilon by 2. Basically n and nk greater than or equal to capital N, so that's why it doesn't matter. xnk minus x less than epsilon by 2, here we have got, so this is also epsilon by 2. I will mention from 1 and 2, from 1 and 2, so which is equal to epsilon. So we proved mod xn minus x less than epsilon. Therefore what can we say? Yes, sequence xn is convergent sequence and converges to x. We will write that thing, make a screenshot of it first. So therefore sequence xn converges to x. So we proved that yes, sequence xn is convergent, but sequence xn was any arbitrary Cauchy sequence. So therefore we can say every Cauchy sequence in matrix space Rd is convergent. Therefore we can declare Rd is a complete matrix space where D is a usual distance. So that all things I have written here, make a screenshot of it, then we will stop. Thank you. Bye bye.